Okay, welcome back. So, if you recall, in our last class, what we were doing, we started with vector fields. We started with vector fields. Okay, and before that, we were dealing with your multiple integrals, and then we also discussed about the change of variables there in multiple integrals. Okay, so today we are going to start a new concept, and it is called line integrals. It is called line integrals. Okay. So here, let me tell you what we are going to do here. If you recall, in single variable calculus, what we did, like say, suppose I want to integrate this function f. I mean, between these points a and b, right? So then, what we did, we just simply divided this interval a b into sub-intervals, right? Through the points, like say, sub-intervals. So suppose if we have n sub-intervals, so then what happens? Here, I will have, like say, I will have run the index I from 1 to n, and then what I would have taken, like say here, in this interval, I would have taken a point, say, xi star, right? And then corresponding to this point xi star, so I would have here, if this is y equal to f of x, so then I would have this height, your f of xi, right? So then xi star to be precise, then what I would have done, I would have multiplied this with the length of this interval, right? And then I would have taken their sum, and then as limit n tends to infinity, right? This being a Riemann sum, of course, f is continuous, we are assuming. So this would have given me the definite integral from f of x from a to b. In fact, this was also an example of line integral. So in that case, this line, it was a straight line. It was a straight line from A to B. It was a straight line from the point A in the real line to the point B. Okay? So now what we are going to do, we are going to consider a different type of line integrals. Okay? So firstly, let us consider these line integrals on a plan. Say, suppose what we are doing here, we are considering a curve like this. Say, suppose I am calling this curve as C. Okay, and let us assume that this curve can be parameterized. By the single variable t in such a way that, what we are going to do, if t belongs to this interval, like, so the curve can be defined by points like x and y, where the coordinates of the point x is a function of t and y is a function of t, right? This we have already discussed earlier. Okay, so now what we are going to do here, and of course I'm assuming that this curve C, it is a continuous curve, and I am also assuming that this curve is smooth. So that means at each point, like say P, we define this vector R such that your RT, it is simply your XTI plus YTJ, then I am assuming that R prime T, this is not equal to this zero factor. Okay, fine. So then you know that a smooth curve is defined in this way. Okay, so that means at each point on the curve, I can have a tangent drawn to it. Okay, fine. So now what we are going to do, because I am parameterizing the curve, with the help of the parameter t, which lies in the interval AB. So what we are going to do, this interval AB, I am going to divide it into, sub-intervals, like as I have told you, just a minute. Draw it something like that. So this is A, this is B. Let me call A as B naught, and let me call B as Bn, and I am going to divide it by these points, okay, and let us divide it into sub-intervals like ti minus 1 ti. Of course, your I goes from your 1 to n. I goes from 1 to n. Okay. So now for each I here, so what is going to happen? Say, suppose this is I minus 1, this is I. So corresponding to that, I am going to get an interval here. I'm going to get two points here. Those 2 points I can call it as pi minus 1. Say suppose this point is pi minus 1, and suppose this point is pi. Okay. So then, if I assume that the length of this sub arc, okay, joining the points pi minus 1 pi on the curve, say suppose it is given by delta S. And what I'm going to do, I'm going to take a point here. Say, let me call it, say, maybe P in this interval. And suppose its coordinates are xi star, y I star. Okay? So that means in this interval, like say that is ti minus 1 ti. Here, I can find a point ti star. In such a way that your xi star is simply x ti star, right? And your yi star is equal to y ti star. Is it okay? Fine. Let me just raise the camera a bit. Till now, is it okay?
Yeah.
Fine. So now, what we are going to do, since now we have, I think, described all this stuff. So basically, again, let me tell what is happening out here. I am giving a curve C, which can be parameterized by the parameter t, which lies between the point A and B, and then we have subdivided this interval AB into sub-intervals. Okay, by inserting points there in such a way that a general interval, this general interval is given by this, and if, like say, corresponding to this interval, I get a sub arc here of length delta Si, right? And then what I am doing, I am taking a point, say, like maybe Pi star or P here, lying in this interval. Let me call it, say, Pi star, whose coordinates are given by this. So now, what I am going to do, if f is a continuous function, of two variables, okay, defined in some domain D, okay, and if this curve C lies in that domain D, so then what I am going to do now, for each of those subintervals, I am going to construct this product. And if I take this sum if I take this sum, okay, so f is continuous, so this is going to be a Riemann sum, okay. So then, if you know that it limit n tends to infinity, this is going to give me, I define the line integral. I define the line integral of the function f of xy, along the curve C as this, okay, and this is nothing but this is equal to this, okay, and you know from the concept of differential, we already defined your arc length function. If you recall what was happening, your ds again, if I express it in terms of x and y as a function of the parameter t, so ds was simply your dx by dt whole square plus dy by dt whole square dt, right? So that means if I use change of variables here, you know that the endpoint of C, it corresponds to when your t equal to a and t equal to b, okay? So then what I can do, I can write this simply as your f of xy, and I'll change that. So instead of ds, I can simply write it as dx by dt whole square plus dy by dt whole square dt, because I have made change of variable. So now I am going to convert x and y as a function of t, and again, since t goes from a to b, this is going to become this. So this is the definition of line integral of a function f along the curve C. Is it okay? Fine?
Yeah.
So what I'm going to do, I'm just going to run through my slides. So this I have already explained how this is obtained. So I have parameterized this curve C, okay, where each point line on C, if it is of the form x comma y, then each of x and y is a function of t, where t lies in this interval AB, and then I'm dividing this AB into subintervals, and the procedure I have already defined. Now, the interesting thing is, so here I have already told you about this, and then I have already told you about this. Like say, I am going to have their n sub-arcs, isn't it? So n sub-arcs, let us assume that they are of length delta S1, delta S2 up to delta Sn, right? So then we are choosing any point pi, xi, yi. This I have already told you in the ith suburb. And if this is important, if f is any function of two variables whose domain includes the curve C, this is very important. So we will f at the point xi star, yi star, and multiply it by length delta Si. So from right now, it may seem that okay, this is simply an ordinary product of two entities, f of x star, xi star and yi star, and then delta Si. But let me tell you, this is going to assume full significance later on when we are going to do your line integral of vector functions. Okay, so and this is the formal definition I have already told you, and then from the arc length formula, this is the length of that curve. Okay, so this is the length of the curve, but if we use the differentiate from the arc length, so this is going to convert it into this. Now, the one interesting thing I want to show you is that If you want to, geometrically interpret what is happening, what actually does this line integral denote, it is nothing but this equation is like this. Say, suppose this is my curve, this is my curve, this is my curve. Okay. So what I am doing here, on that curve, at each point I am considering this height. This height is nothing but f of xy. So what is happening out here? Say suppose I am enacting a fence here. It is not necessarily that the fence is of unit height. Are you getting my point? I am erecting a fence along the curve. Okay. And if it has different heights, and the height is nothing but given by function f of xy. So it is simply going to denote the surface area of that fence. Is it okay?
Yeah.
Fine. Okay. So now let us see how we can work out examples. So let us start with a very simple one. Is this blackboard is clearly visible? Because I have switched off one light.
Yeah, it is visible.
Okay, thanks. So suppose you have to perform this line integral, and where C is nothing but your upper half of the circle, this one, x squared plus y squared equal to 1. Now, suppose it is the upper half of the circle, x squared plus y squared equal to 1. See, whenever you think about this line integral, firstly you have to think about the parameterization. Okay, fine. So now it is pretty straightforward here. Because what I have something like this. Okay. So this is my C. Okay. So right. So I have to perform integration along this curve C. Right. And you know that C can be parameterized by your x equal to cos t, right? And y equal to sin t. Okay. And because this is simply your a to b, this is your simply a to b f of xt yt square root, dx dt whole square plus dy dt whole square dt. So now you can see that if you want to compute this is simply dx dt. It is your minus sin t, dy dt is cos t. So basically sin square t plus cos square t square root. That is simply 1. Is it okay? Fine?
Yeah.
So, and again here, because this is upper half of the circle, your t goes between 0 to
Pi.
0 to pi. So a is 0, b is pi, and this one, if you convert it into as a function of t, so this is going to be 2 plus cos square t sin t dt, and this is straightforward, like 2t, because minus sin t is the derivative of cos t, so this is going to be cos cube t. Am I okay? So you simply perform this. Okay, so you are going to get 2 pi minus 1 by 3. So minus 1 minus 1. So 2 pi plus 2 by 3. Okay, it should give you 2 pi plus 2 by 3. You check it. Yeah. Okay, because cos pi is minus 1, again minus cos 0 is again 1. Okay, fine. So then I've already done. So now let us come to integral along your piecewise smooth curves. Line integrals along piecewise smooth curve. Okay, so what is it? It is, I mean, very easy. See, earlier we had assumed that that curve C along which we were performing line integral, it was smooth. It was completely smooth. But what we can do, we may assume that okay, the curve is piecewise smooth. The curve is piecewise smooth. It may be something like this, Okay. Say suppose the curve is such that it is something like this. Are you getting my point? It is something like this. It is piecewise smooth. Okay, it is smooth only along certain portions. Okay, and here in this particular case, you can see that your C is nothing but the union of C1, C2 up to C8. Okay, and then your this is simply your, say suppose it is union of I mean say n curves which are smoothed themselves individually so that the entire curve C is piecewise smooth. Okay, so then this is given by C1 That's it. It is as easy as this. So basically, what you have to do, you have to, I mean, express it as a sum of, express it as sum along those curves which are individually smooth, Okay, fine. So let us try to work out one example.
Sir,
Yes.
will you please mention about the orientation of the curve?
No,
the arrows that you're drawing.
Yeah, that I will do at the end. In between, I'm going to tell about it. Yes, that is an important thing because orientation. Because I'm going to do that orientation for a curve where I am using some arc length. Okay, then what I'm going to do again, I'm going to define line integrals along x and y axis, and I would like to distinguish between them, and then I will tell about the orientation. Okay, fine. That thing I will do. Definitely, this is going to be an important factor. Okay, because I would like to point out that if you consider, I mean, line integral with respect to arc length, the orientation is not going to change the value of the integral. Okay, but if you are going to perform it along a straight line, the orientation is going to change the value of that integral. That happens. Okay, let us consider one example. Okay, it is a straightforward one. Okay, say suppose See, let me tell you one thing. Here, you don't have to, worry too much about the integrand. Okay, because integrants somehow they can be handled. Here, the only thing is that you simply look at the curve, okay, and how it can be parameterized. So here we have to integrate this where C is given by what? Given by C is nothing but the union of two curves. Okay, and where the first curve C1, it is the parabola y equal to x squared. Your between the points 0, 0 and 1, 1. Okay, and C2, it is the vertical line. It is the vertical line. Your between the points, your 1, 1 and 1, 2. 1, 2. So let us not even look at the integrand. Let us firstly try to deal with the curve C. Okay, fine. So what is that? Okay, so okay, if this is x, this is y. Okay, so this is my C1, okay, and this vertical line, this is my C2, right? So this is 0, 0, then this is 1, 1, then this is 1, 2. Is it okay? Fine. So then obviously, your this is simply going to be C1 2x ds plus C2 2x ds. Okay. So now here look at this. So now it is all about parameterizing the curves. So if I look at this curve, what I can do? I can simply plug in say x equal to t, so that your y equal to t squared. Is it okay? Isn't
Yes.
it? My parameterization will be given by
Yes, sir.
So that is why here the first integral, and then what is going to happen? So this is 2, x is t, and then what you have dx dt whole square. Here dx dt is 1, okay, dy dt is 2t. So that means it is plus 4t square dt. And I have given x equal to t, and here you can see that x goes from 0 to 1, isn't it?
Yeah.
Yes, sir.
So this is going to be 0 to 1. So this is about my first integral. So now in the second integral, let us come here. So here you can see that your x is fixed. X is fixed, isn't it? So along this line, your x is simply equal to 1. Fine. So what we are going to do? We are going to use x equal to 1, y equal to simply t as my parameterization. Is it okay? Fine.
Yes.
So then what is going to happen? Because y is t, now 2x, it is going to be 2 into 1. And again, if x is 1, dx dt is 0. If y is t, dy dt is 1. So this dx dt whole square root dx dt whole square plus dy dt whole square, it is simply going to give me 1, isn't it? Right? It is simply going to give me 0 plus 1. So, and then dt. And since t equal to y, and you can see that y, value of y, it goes from 1 to 2. So here, my limit is going to be 1 to 2. That's it. Is it okay? Fine. And the remaining stuff you can easily do. So what I can do is 2t, because 4t square, its derivative is 8t. So what I can do, I can write it as 8t So then this is going to be 1 by 4, then 1 plus 4 t square to the power 3 by 2, and then into 2 by 3, 0, 1, and this is simply going to be 2 t12. So you just simply plug in these values you are going to get.
That limit is going to be different. 0 to 1 is not the limit.
Which one?
This first integral limits. No, when you make this change of variable.
No, because no. Just wait. It is going to depend on, because the limit is for t. Limit is for t. T equal to x here, and x in this particular case it goes from 0 to 1.
Yeah.
Right? Okay. So you simply integrate it, you are going to get the answer. I think this is something like 1 by 6 5 root 5 minus 1 and then plus 2. Okay. So it is about line integral along piecewise curve. Do I have more? Okay. Now let us come to line integrals along x-axis and y-axis. Okay. Or what they do, they simply write it as line integrals with respect to x and y. Line integrals here with respect to x and y. Line integrals with respect to x and y. So here, I mean, still we are dealing with that curve. Huh? Remember, here we are still dealing with the curve, but it is going to be slightly a bit different. But before that, I'd just like to show you slides regarding your application of your line integral. So this we have already done. See this one. See mass and center of mass of wire. So you know that I mean mass. I mean what is density? Density is nothing but mass per unit volume. Okay, fine. So I mean if you integrate the density as a volume integral, so you should get like say what you should get the mass. But here, what we are going to do, we are going to assume that the wire it is of unit cross section. Okay, so then it is what we are going to get if we integrate the density as a function of x and y over its whole length. Okay, so then we are going to get the mass. So this becomes the formula. Mass is equal to simply what you do if the wire is in the shape of a curve. So that curve is C, it is given by this. Okay, and again this has been obtained by considering the moment. Okay, so the center of mass is given by this formula. So I'm giving an example here. And again, in your tutorials, there are going to be examples, so I don't want to spend much time on this. So now, next time, what I'm going to do, I'm going to deal with your line integrals with respect to x and y. Okay. So here, line integrals with respect to x and y. This is simply your fxy dx. Okay. So here, how it is obtained? This is nothing but earlier what we did. Your c fxy, your ds. So this was what? This was your limit n tending to infinity, I goes from 1 to n, then f yi, okay, and then into delta si. You know, I mean all the entities here, what they are. Okay, so now here what I am going to do, if instead of this delta si, if instead of delta si, if I do this I assume to be xi minus 1, where your simply xi is x of ti, your xi minus 1 is your x of ti minus 1, x of ti minus 1. So then here defined as this. So I from 1 to n, f of your xi star, yi star, and then this is delta xi. Okay, and similarly, I mean, if you consider line integral with respect to y, what we do now, we simply consider delta yi. We simply consider delta yi. So xi yi star is delta yi, and you know what is delta yi? It is simply yi minus yi minus 1. And again, likewise, this yi is going to be y of ti, and yi minus 1 is going to be y of ti minus 1. Is it okay? Fine. Now, the only thing is that here again, what we can do now, again, once you know the parameterization of the curve, so then what you can do, this you can change to f of xy, and this is dx dt. Okay, so that is why it is the formula is simply written as this: xt yt, and again it is going to go from a to b. Okay, similarly for this also I am going to get y prime t dt. Is it okay? Fine. Let me just show you the formula here. So this is what it is, as I have told you. This is going to convert it into something like this. Okay. So now let us for example how to work this out. And see, this is simple. Earlier, I mean, what you have to do. I mean, your ds was, I mean, square root dx dt whole square plus dy dt whole square dt. Now here we have to deal with giving a simpler function, right? Simpler, I mean, differential dx and dy. Earlier it was ds. Okay, so let me just I mean, note it down the problem. Okay, please see your y squared dx plus x dy. Okay, and it is saying is that your c equal to c1 first, then c equal to c2, and c1 is the line segment from -5 -3 to your 0 2, and this is given by x equal to 4 minus y square, and again from the same 2 0 2. Okay. So again, please don't confuse with union of curves. Okay, so here we have to evaluate two integrals. So basically, we have to evaluate, I mean, this integral along the curve C1, and then again this integral along the curve C2. Okay, so here the -5 -3, right? So let us 3, 4, 5 -5 -3. Let us make it small. 1, 2, 3. So this, and then this is 0, 2, 0. Okay, so this is C1. So this is -5 -3. This is 0, 2. And this is 4 minus y squared. 4 minus y squared. So your minus y squared is going to be something like this, isn't it? 4 minus y squared, you have to move it 4 units towards right. Fine, is it okay? So it is going to be something like this. It is going to be something like this. Is it okay? That is the way of drawing it easily. Okay, fine. So let us consider the first one. So let us first consider C1 y squared dx plus x dy. Okay, fine. So here let us consider this. So if you look at this, what we are going to do, we are going to find out the equation of the straight line passing through those 2 points. Okay, so the equation is what? Let us consider this. So it is going to be y minus 2, then the gradient will be given by your -3 minus 2 minus 3 minus 2 divided by your -5 minus 0 and then x minus 0. Okay, so then you will see that this is -5, this is -5, this is 1. So basically here you are going to get y equal to x plus 2. Is it okay? Fine. I'm talking about c equal to c1. Is it okay?
Yes.
Fine. And
Yes,
then the easiest way to parameterize is what? Simply you take x equal
It's
to
equal
t,
to t.
then y is going to be equal to what? T plus 2, right? And again, you can see that x goes from -5
Minus
to
5 to 0.
0, right? So here, if I want to change it, it is going to go from -5 to 0, and then y square, this is simply going to be t plus 2 whole square, and then since x equal to t, dx is going to be equal to dt, right? Then again plus x is t, and y is again t plus 2. Y is again t plus 2. So dy is you simply dt. Fine. So simply integrate it. So t square plus 4t, right? T square plus 5t plus 4. Simply integrate it. That's it. Okay, you can easily do it. It's very straightforward. So now let us come to your C2. Let us come to C equal to C2. So if I consider C equal to C2, this one, because this is already been given, x equal to 4 minus y square. X equal to 4 minus y square. So it is easier for me to parameterize it as y equal to t. Yes, x equal to 4 minus t square. Is it okay? So then this along C2. Now your y squared. So it is simply half. And since say t is y, and y goes from
minus 3
3
to
to
2.
2. So here limit is going to be minus 3 to 2. Y is t squared. Now dx is going to be minus 2t dt, isn't it? So dx is minus 2t dt, and again x is 4 minus t squared, and dy is simply dt, and again simply do the stuff. So it is simply going to be minus 3 by 2 minus 2t cube minus t squared plus 4 dt. Simply integrate it. That's as easy as that. Okay, fine. Now, that sometime back I was told that I should talk about the orientation. So this orientation again, I mean, we will have to deal with orientation repeatedly. Now, let me tell you about the orientation thing. And again, before that, let me tell you one thing. Like here, we are talking about, line integrals, with respect to x and y. So then, what we are going to call, line integrals earlier that we have defined, line integral along a curve. So maybe that can be said as line integrals with respect to your arc length. Okay, so whenever we say line integrals with respect to arc length, so we are going to consider ds. Okay, fine. So now let us see how the orientation of the curve is going to affect the value of the line integral when you consider line integral with respect to arc length and then line integral with respect to x and y. Okay, so I am simply going to read it out and then explain the stuff to you. Okay, so here you see what is happening. So firstly, what I am doing, I am considering a curve. I am considering a curve AB. I am considering a curve AB, and suppose it can be parameterized. It can be parameterized through the parameter t, which lies in the interval small a, comma small b. So that means if the coordinates of capital A is xy, so then x is simply x of A and y is simply x of y of A. Is it okay? Fine. Similarly, for the point B, if again its coordinates are xy, so then x is a function of B and y is a function of B. So, and let us assume that its orientation is this way, as the arrowhead suggests. Now, if we consider the same curve, now the orientation is different. So then it is denoted by minus c. It is denoted by minus c. Okay. So then, what is going to happen? What is going to happen for the same interval? If I consider the line integral with respect to arc length, so then what we are going to do? We are going to divide it into sub arcs. Okay, and then we are going to simply multiply the value of the function corresponding to a sub arc. Okay, and then we are going to multiply it by the length of that sub arc. Okay, so that was our idea. So now what is going to happen here? In that particular case, the value of the integral is not going to change. Okay, value of the integral is not going to change. It is going to remain the same. Now, when I talk about line integral with respect to x and y, so then what is going to happen? Line integral with respect to x and y, I was considering what? Your f x star y star delta xi. Okay, fine. And if I consider line integral with respect to arc length, I was consider delta xi. Now look here, what was happening? Say if this is the interval I am talking about, if this is the arc length I'm talking about, so then this point is your pi minus 1, and it is given by x ti minus 1 y ti minus 1, and this point, if it is pi, it is given by x ti y ti. And remember, whether I am considering this along this direction or along this direction, this delta si simply represent the length of this arc, length of this star. Okay. So now whether you come from that side to this side, this is not going to change. Delta si is going to remain delta si. Okay. This is simply a measure of the length, and it is going to be always non-negative. Is it okay? On the other hand, if you recall delta xi, it was simply xi minus x I minus 1, xi minus xi minus 1. This is x ti, this is x t I minus 1. So now the same thing if you move from that. Okay, so you are going to consider the interval delta xi because you are coming from now right to left. Okay, so you are going to get xi first, after that xi minus 1. So this is going to be xi minus 1 minus xi. Okay, right? So in that case, the value is going to change. It is going to be simply negative of that. You should remember that. Okay, so with that note, we are how much time do I have? Yeah, I still have around 10 to 15 minutes. So now I am going to do line integral space, and then I'm going to move over to line integral of vector function, which is a very interesting concept. So now for line integral space, it is the same thing. Because whether you consider this curve C in plane, in xy plane, or in xyz space, it doesn't matter. Only thing is that here, if I consider a point P, xyz, now it is going to be parameterized by xt, yt, zt. But, and again, now my line integral will be denoted by this, and you know that, and in 3D space, I mean, if I want to parameterize it, so then ds, it is simply your dx dt whole square plus dy dt whole square plus dz dt whole square dt, isn't it? So what is going to happen? So this one, it is simply going to be, and again, if t lies between a and b, it is simply going to be a to b f of xt, yt, zt into this. That's it. Is it okay? Fine. So now let us work out. So basically, I mean, then the point P, we are going to consider the vector joining the origin to the point as R, and R is going to be simply xi plus yj plus zk. Okay, so let us just try to work out one example. I think it's pretty straightforward. I think I don't have to work up any example, right? It's pretty straightforward. You will be given a function f, you simply parameterize it, right? And then just plug in this. It is pretty mechanical. Okay. So rather, I would like to go to line integral of vector fields. Line integral of vector fields. Okay. Line integral of vector. Okay, so if you recall, I mean line integral along a curve. So what we did, simply we were considering a scalar function. Remember, this was a scalar function along the curve C. So now, instead of small f being a scalar function, so what we are going to do, we are going to consider a function which defines a vector field. Okay, fine. So basically, this is going to be something like f1 xyzi plus f2 xyzj plus f3 xyzk. Okay, and I am going to consider the integral of this function again along a curving space. Again, so with a curving space, say suppose this is C as well. Okay, fine. I'll come back to this. Let me ask you one question. Say, suppose this F denotes the force. Earlier, what we did, we considered say some mass or something. Say, suppose this is the force, and if it moves some say object from the point A to the point B along a straight line, right? Then the work done by the force is simply what? The dot product of the force and the displacement vector. Is it okay?
Yeah.
Fine, right? Now, what we are going to do, we'll be interested to see if instead of the force moving an object along a straight line, if it moves along a curve, what is going to happen? Here, is it okay? Everybody, fine. So
Yes.
that's what I'm going to do. Okay, fine. So let us start. So as before, what we are going to do, I am going to assume that this curve can be parameterized through this representation. So RT is simply xt, yt, zt, and your t lies between A and B. Okay, and as before, what we are going to do, so this interval AB, I am going to subdivide it into sub-intervals. Okay, by the points, I mean say A is say T0, this is equal to Tn, by the points T0, T1, T2 up to Tn, where I mean this is the representative in the sub-interval. Okay, and here I goes from 1 to n. Okay, and as before, what we are going to do, corresponding to each of this sub-interval, we are going to get a sub-arc here. Is it okay? So consider this sub-arc whose initial and final points are simply pi minus 1 and pi. So pi I minus 1 corresponds to x ti minus 1, y ti minus 1, z ti minus 1. Similarly, pi is also like that. You already know the formula. And then in this sub-arc, which is of length say delta si, we consider a point pi star, again whose coordinates are given by your xi star, yi star, zi star. Okay, so that means there exists some point ti star belonging to this interval, belonging to this interval, okay, such that xi star equal to your x ti star, similarly for yi star and zi star. You know that. So now let me concentrate on this sub. Okay, so that is why I'm separating it out. Okay, suppose this is my situation. Let me take it here. Yeah, it doesn't necessarily have to be individual. Now, if
so that is pi star.
Yeah, sorry. Yes, this is pi star. Sorry. So now, see here, and remember this arc. It is very small, although I have magnified it. It is of elementary length. Okay, so delta Si is extremely small. So basically, if your Pi corresponds to the vector Ri and Pi minus 1 corresponds to the vector Ri minus 1, so this is almost given by delta Ri, where delta Ri is simply Ri minus 1. Okay, fine. So now what is happening out here? So if I want to find out the work done by the force, say suppose I consider a vector field given by this at this point pi. So if I consider this, if this is the force applied at this point, this is the force applied at the point pi star, and suppose I want to find out the work done by this force F in moving the particle from pi minus 1 to pi, or moving an object, moving not the particle, moving an object situated at pi minus 1 to pi. So then what I must do, the direction of that object is given by its tangential direction, isn't it? Right? Okay. If I assume that t bar is a unit vector, drawn at the point pi star, right? So then, if you want to construct a vector, something like AB, which was the displacement vector. So how do I get the displacement vector completely? It is simply length of this vector into a unit vector along this. Isn't it? Is it okay?
Yeah.
So likewise, if I want to get the displacement vector along this subarc, which is of extremely small length, so that is going to be given to me by the length of that arc into the tangent vector along that. Is it okay? Fine. So that means if I take dot product of the vector field, which is nothing but the force, dot product of the force along this vector, it is going to give me the work done. Clear?
Yeah.
Right? So now what we are going to do, I am going to add all such entities along those, I mean sub arcs. Okay, so that is going to give me something like this. So x star, y star, this z star dot t, and let it be simply t. I am not really worried about it because you will understand. Delta si, and if I take this summation, and if I let the number of sub-intervals can be infinity, so this is called, in fact, this is called the line integral of the vector field, along C, and it is written as this. Is it okay? Fine?
Yeah.
Yes, sir.
Yeah, you have understood the underlying concept behind constructing the definition, right? Okay, so now what I would like to introduce you to different forms of this. Okay, fine. So now suppose I mean at this point Pi star, suppose I mean I can parameterize it with the vector r1. Okay, or simply you take any point say P whose coordinates are x, y, and z, and suppose it is parameterized by this RT is simply your xt, yt, zt. Fine. So then you know that a unit tangent is simply given by r prime t by this magnitude of r prime t. Isn't it? Is it okay?
Yes.
Yes, sir.
Fine. And again, if you recall, ds, it is fine. Okay. And what is this term under the, I mean, square root? This is simply mod of r prime t, isn't it? Right?
Yeah.
So that means if you want to make change of variables here, say f was a function of x, y, z, and again x, y, z themselves were functions of t. So then this is going to be, because t goes from a to b, and then f is simply a function of xt, yt, zt dot your r prime t mod of r prime t, fine, and your ds, it is what? R prime t mod of r prime t, this, fine. So then this is simply going to give you a to b f dot your r prime t dt, isn't it? Eventually f is going to become a function of t. Is it okay?
Yeah.
Fine. And in fact, this is also I'll give you, I mean, slides. This is also, that is why this is also written simply as f dot dr, f dot dr. Because dr you can write it as dr dt into dt, and dr dt is simply r prime t into dt. So that is why this is also written as this. Is it okay? Fine. So let us run through the slides so that I mean it serves the purpose of revision as well as some better understanding. So, in fact, in these slides, I have explained everything. All this stuff I have already explained. So, what we have done, we are considering a curve C in 3D space, okay, which can be parameterized through the variable t, which lies in the interval AB, right? If A is, A is the point, initial point, so that is P naught. P naught corresponds to t equal to A, Pn corresponds to t equal to B. And as before, we are dividing this curve into some sub-arcs, okay, through the introduction of those sub-interval of AB, and you know how it happens. So then what we are going to do, as I have already explained, so in this sub-arc, between the points pi minus 1 and pi, we are considering a point pi star, okay. There we are considering the force F, which is a vector value function, and if I consider the tangent vector t at that particular point, which corresponds to ti star, so then what happens? I have already explained. So this is what happens. Let F be a continuous vector field defined on a smooth curve C, given by a vector function rt, and t lies between A and B. Then the line integral of f along C, it is given by this expression, f dot dr. And in fact, the meaning of this is this. I have already explained to you. So you can write it as either this or f dot t dr square. T is the unit tensor vector at the point x, y, z on C. Okay. So in my next class, I'm going to do like some exercises. So then I'm going to move to fundamental theorem of integral calculus for this vector value function, which is going to have a lot of application. Okay. Till then, I'll see you in the next class.